reactants converting to products. In these reactions, we want to know, in kinetics, we want to know how fast a reaction can take place, or what is the speed of a reaction. So this can be written as a rate is equal to losing reactants over time is equal to gaining products over time. Now, we can also write rate is directly proportional to the molarity of the reactants and nothing to do with the products. So therefore, rate is equal to K to the reactant concentration. K is the rate constant. The power here is 0, 1, 2, 3. We call the order of the reaction. So we're going to compare them. To go there, let's graph the reactant molarity versus time. So the time could be seconds, minutes, days, and years, what is suitable for that measurement. That's time is the x-axis. And in the y-axis, you have the molarity of the reactants. So we know typically it's going to lose like that. And that's actually depending on the rate, it could be different. So we're going to look at a way or compare these rates and orders. Okay, so I'm going to think reactants are big A and the products are big B. So we're going to focus on the A concentration, the reactant concentration. The first thing is a rate law is typically, that's actually the differential rate law. And for the 0th order, rate is equal to K to the 0th power of A. That's the molarity of the reactant. So that means that is 1 actually. Anything 0th power is 1. So therefore rate is K to the 1. So first order is rate is K to the A molarity, but it's first order. So therefore that's actually K to the molarity of A. So second order is rate is equal K to the A second power of 2. So that's how 0, first and second order differential law. We're going to look at the integrated rate law. So that's actually A equals to negative KT plus A molarity. It should be written A squared is equal to negative KT T for time and plus A naught. And then in the first order, it's ln A is equal to negative KT plus ln A naught. Okay. And then the second order is 1 over A concentration KT plus 1 over A naught. So that's how we write the integrated rate law. So make sure they all are actually A naught, because initial molarity of each scenario we should be taking. When I show the math, I'll show you. And also linear equations are y is equal to negative mx plus c or b, y is equal to negative mx plus c, y is equal to positive mx plus c. That's how we write it. The slope here is negative m, positive m. So therefore, this should look like in a graph, negative slope and the negative slope for the first order and positive slope for the second order reactions. That's how you know. But what's the difference is the y-axis. You see, first one is A molarity, second one is ln A. Then the last column is 1 over A molarity. That's y-axis is different. Now, we're going to look at the units of rate constant. That's an important one. This is how you do it. So rate is measured molarity over seconds. So that means K is molarity over second. You can write M as -1. So here M over S is K and A also M to M cancels out. So therefore, for the first order, K is 1 over S, that is also S -1 to the power. Okay, here the last one, the second order, m over s is equal to k m to the squared. In this case, the m to the squared cancels out. You have k is equal to 1 over ms. You can write a slightly different way using moles per liter too. Now, the last one, the t half for the 0th order is A concentration divided by 2K. That's the rate constant. For the first order, T half is ln2. That is also 0.693 divided by 2. The second order T half is 1 over K, and A concentration, the initial A concentration. That's how you compare those. Look at for my problem solving.